Okay, so new section for today. We're talking about section 5.5 on change of variables. This is a really big section, just in terms of the number of pages and the number of things that are going to need to get said. This is going to take us several lectures to finish. So maybe we'll finish by Wednesday of next week. We'll see. Okay. So anyway, we're going to start off by segueing into it by going back to single variable and talking about the substitution rule. I hope everybody remembers the substitution rule. I assume and presume that you do. So here it is. This is the formula, anyway, for the substitution rule. And you may previously have understood the substitution rule as a method. It's you're allowed to do the following, right? But this is a way of just writing that down as a formula. So lots that you can say about this. First thing I want to say is you can think of this as an algebraic thing. I want to first think about this as a kind of a sort of a geometric statement. In particular, that we have our substitution function g. Think of this not in terms of the formula that you write, but think of that as something that takes points on the t-axis and then returns, points on the x-axis. And I want to think about it, in terms of what that looks like, which, usually is not how it's done when you're talking about substitutions. And of course, when I say that this is what the substitution function does, points on the t-axis are taken over to points on the x-axis. Or similarly, and for morally the same reason, an interval on the t-axis, right? Every point in the interval, and therefore the interval itself, gets taken over to become a new interval on the x-axis. Okay, so there's that. Seems like an odd point of view. Why are we taking an odd point of view on something that we already understand? I'm going to give you the usual reason. Usual reason is that, what I like to do in multivariable calculus is find a single variable analog, take the point of view on the single variable analog that most naturally extends to the multivariable context, and then make that extension, right? So that's what we're building up toward here. We're going to take a point of view on substitutions that we can naturally extend to multivariable. All right. So now there's two other aspects that I want to hit on how to think about substitutions. I want to talk about this idea called a pullback. So on the one hand, points, when you have a function, right? The function g that goes this way, points go that same direction. One might say points push forward because they go the same direction the function's going. Right? I claim, though, that there is this thing called pulling back. There seems a weird thing to say, but expressions go backwards through the function and doesn't look relatable until you consider the following. Let me show you a sort of an easy, silly example. Suppose you have a function going this way from, let's say, the t-axis to, let's say, the x-axis. Not that it really matters. And let's suppose my function is that x is t cubed minus t, whatever. Right? Some formula like that. How would I rewrite cosine of t? How would I write that in terms of x? Answer, I don't know. That's tough. I don't know. Have a formula for t. I can't plug in for t. I don't have a formula for it. I can't solve for it. Not clear how this would work. However, going the other direction, if I have some expression like, tangent of x, how would I write that in terms of t? Nothing to it. Nothing to it. This expression, written in terms of x, pulls back through the function just by plugging in. It's easy matter of just plugging in what x is, and after all, x, let's see here, x is t cubed minus t. Right? So this is what I mean when I say expressions pull back, right? Points go the same direction the function's going. In fact, that's what we mean when we say a function goes a certain direction. Expressions go the other way. Does everybody buy it? Everybody see what I'm talking about? I mean, once you see it, it's really not that deep of a point. This is just what happens when you plug in. It's just, I'm just sort of making that observation explicit. Okay. So that's the way I want to view what's happening here with the substitution rule. I want to view the substitution rule not so much as two things that are equal to each other, and let's just leave it at that. Let's view it as that if I have an expression on the right, specifically an integral on the right, an integral on the domain that is this output domain, you might say the image domain, over here on the right. An integral on the right can be pulled back and rewritten as an integral on the left. Okay, so that's that point. And now next thing, I want to talk about the stretching factor. This business about pulling back, again, is mostly just a matter of plugging stuff in, nothing deep. For example, if x is g of t, then, well, we just literally toss that in there. Just literally plug in everywhere you see an x, just put g of t, no problem. But there is the annoying little matter of what to do with dx. What is dx on this picture? And again, different points of view you can take. Again, I want to push a particular convenient point of view. I want to think of dx as being, well, dx is, you might say, this size. It's the size of this piece of the x-axis. I want to think of it a little bit differently, not as a size. I want to think of it as a change. A change in the value of x. We were here, now we're here. Right? It's not that different of a concept. So dx I want to think of as a change. And I'll point out that dx, thought of as a change, is literally the output change that you associate to this corresponding input change, dt. Right? Let me just be consistent here. If you have an input change dt, that gives rise to an output change dx. And let me remind you, and you probably already noticed, you hear me say input change and output change. One of the big points of view that I push on derivatives is that that's what a derivative is. It's a relationship between input changes and output changes. So the derivative is this thing that you multiply by the input change to get the output change. Is that cool? So we had a little piece of the t-axis, some size, whatever. Its image over here on the x-axis is, well, at least as I've got it drawn here, bigger. And it's bigger by a factor that I can quantify. And so when you take something and make it bigger by multiplying it by a factor, I think it's pretty reasonable to call that a stretching factor. This says how much bigger does my dt get when I translate it appropriately into seeing what dx is. Okay, how are we doing? This is what I mean by a stretching factor. All right. Okay, so that's the context. Now, what we're going to do is try to do morally the same thing in 2 dimensions. So here's what that picture looks like in 2 dimensions. Instead of having a function, a single variable function with one input and one output, now we've got a function that has a 2-dimensional domain and a 2-dimensional target. All right, so this is a multivariable vector-valued function. By the way, very quick aside, in order for what I'm going to set up here to work out kind of conveniently and consistently, I do need these dimensions to be the same. In fact, for the moment, 2 specifically for both the input and the output. And we'll talk later about what happens in 3 dimensions. I can talk about having an integral expression over here. And I can talk about what would it mean to pull that back. And again, pulling back just means plug it in. most of what happens when you do a pullback is just taking the formula where x and y are g of u comma v, and just tossing that right in here. X comma y is g of u comma v. It's just the act of plugging in. But there is the one little additional kind of sticky wicket, and that is that we do have to recognize that this little piece of the domain over here, my pullback domain, you might call it, that little piece, that collection of u comma v's, if I plug them into the function, what's going to come out is going to be some other shape over here. It's going to be, probably not going to be a rectangle. This function g changes things a lot. It might stretch them or rotate them or twist them or shear them. There's lots of things that can happen. So this shape here, we'll talk about exactly what that shape is later. But more to the point, we don't expect it to be the same size. We expect it to be, well, it's different. It's all stretched out. Just like here, we don't expect dx to be the same as dt. Of course not. Right? Likewise, we don't expect this area to equal to that area. And so again, if I am going to rewrite everything in terms of u's and v's, I need to know by what factor do I multiply the green sort of input area differential, du dv. By what factor does that get stretched out? How much bigger is the output area than the input area? And this, again, is what we're going to call the stretching factor. What that stretching factor is, I'll reveal in a couple of minutes. But for the moment, it's there. I'm just going to say, this is how you interpret the stretching factor. It's just how much bigger is the output area than the input area. Is everybody good so far? Okay. All right, so all together then, details to follow, of course, in the same way that you can think of a substitution function as allowing you to pull back an integral in the target space into an integral in the pullback space, the pre-image space, however you want to say it. In the same way that an integral here turns into an integral there, likewise, in the two-dimensional setting, if you have a multivariable, what we call change of variables function, then an integral on the right can pull back to an integral on the left. And here's why we care about this. Here's the big win of it all. Notice that if I start even with a nice domain here, right, nice pretty rectangle on the left-hand side, yeah, but over here on the right-hand side, the image of that rectangle is, who knows, it's going to be weird and curvy and bumpy and undesirable. It's going to have corners all over the place, right? I mean, imagine the process of slicing this up. You're going to hit that corner as part of your slice, and you're going to hit this corner, and then, oh my gosh, I think I'm going to hit that corner too. I mean, nightmare, right? This is a terrible domain to have to do an integral on. So the prospect of being able to take this integral on the right and, and being able to pull it back, and instead having this integral on the left, where my domain is just that original rectangle, extremely desirable. Right? Domains, as y'all know, make a big difference in multivariable integrals, and having an undesirable domain over here on the right, being able to turn that into a much more desirable domain here on the left. Big win. Makes our life a lot easier. Everybody on board? All right. So that's the plan. All right, let's talk about the stretching factor. What is that stretching factor? I'm just going to assert it. I'm not going to prove it. Here it is. The stretching factor is the absolute value of the determinant of the derivative matrix, aka the Jacobian matrix. That's the formula. Where does that come from? We're going to talk about that later, realistically probably on Monday. I'm probably not going to get to it today. The reason I don't want to talk about it now is because we've got enough going on with this concept as it is. It's a pretty big idea, turning an integral on one domain into an integral on a totally different domain. It's a lot to keep track of. There's lots of kind of versions of this. I want to get a kind of a working understanding, working proficiency with it first. And then once we kind of see how it works and can kind of, get problems solved, then we'll go back and talk about why it works. Okay. All right, so elaborating on this formula, don't forget the Jacobian determinant. The Jacobian matrix, derivative matrix. That's all it is. It's a matrix consisting of the various partials of the various outputs with respect to the various inputs. Right? Organized in that certain way. Here's another bit. This is just a notational thing, but I think this is a really nice piece of notation. Not the matrix itself now, but if I talk specifically about the determinant of this matrix, very convenient way to rewrite that is with this notation right here. Now notice this does not involve the absolute values. I'm deliberately leaving out the absolute values. Just the Jacobian determinant on the inside. I'm going to rewrite with this weird notation right here, partial x comma y over partial u comma v. And it's going to take me a minute to explain where this comes from and why I like it so much. But here we go. First of all, inside of this matrix, you'll notice we're taking the partials of x and y. So partial xy, you might say, is just kind of a streamlined, convenient way of saying I'm going to take the partials of x and y. And then what am I taking the partials with respect to? Well, u and v. So partial uv on the bottom. So again, streamlining it, we're describing, roughly speaking, this matrix as the partials of x and y with respect to u and v. So that's kind of plausible, I think. Everybody buy it? Now, there's the little matter of, well, yeah, but again, this is not the matrix. This is the determinant here. It's the scalar value of the determinant. And good news, that actually makes even more sense because, look, this written as a fraction looks like it ought to be a scalar. Right? So that actually, that's actually sort of good news, not bad news. One could argue. There's one more reason that I really like this notation, and I'm going to show how this plugs into the formula. Don't forget what we're talking about here is my stretching factor. So that's what this thing is. It's the stretching factor that sticks in there. And let me now write down. Let's see here. Stretching factor here. Partial xy. Partial uv. There's that stretching factor. Let me write down now here next to it the du dv that I'll be multiplying it by. And of course what that's supposed to end up equaling is this thing over here, area on the right hand side, which I'm going to call dx dy. And now I claim that this is actually kind of nice as follows. Take a look at what we have over here on the right. On the left, I have a du dv. In the denominator, so it appears, down here, I have something that it kind of smacks of du dv. It's not literally du dv, but you can see the u and the v both there, and you have this temptation, this, you kind of want to cancel those. Of course you can't. It's a major math crime. It's not really a thing. After all, don't forget this thing that I've written as a fraction, it's not a fraction. It's a determinant. So there is no fraction. There is no cancellation. This is just a kind of a memory tool or a satisfaction thing. It's not a mathematical argument. But if you do cancel the UV, note that what's left over is the XY. And so it kind of looks nice. in that sense. Does that make sense? And again, a full apologies for the fact that this is, strictly speaking, nonsense. But it looks nice on the page. It served well as a memory tool. If you at some point find yourself confused, wait a minute, the partial xy, partial uv, do I multiply that by the dx dy or do I multiply that by the du dv? You multiply it in the way that makes the apparent but nonsensical but still apparent cancellation actually work. So, very nice little memory tool. Questions on that? Cool. All right. Cool. So, let's do one. I want to compute this integral right here. Integral over this domain over here on the right. What I like to call my image domain. Let's recognize for a moment that this domain is horrible. Right? I really hate this domain. After all, if I were to come at this from a, head-on, just, slice it up, iterated integrals kind of approach to compute this double integral, what I would have to do is decide whether I want to slice like this, in which case I hit a corner here, and then I keep slicing, I keep slicing, and then I eventually hit another corner here, but I'm still not done, and so I have to keep slicing like that until I'm done. I would have to therefore break this up into 3 separate integrals, and nobody wants that, right? You could say, okay, well, how about if I slice it in the other direction? And again, you hit the same 2 corners, just kind of in a different way, different order, I guess. But still, you hit 2 corners, you have 3 integrals. Nobody wants this. Okay, so bummer of an integral that we face here. Now, in this question, I'm going to confess this is a manufactured example. I'm going through this manufactured example because I want to show you the process. I don't want to get distracted again by side issues and annoyances that we will learn how to deal with as we go on. And so in this manufactured example, I'm giving it as free information in the statement of the question that my output image domain is literally the image by way of a given change of variables function, right? Given in the statement of the question, right? Don't get used to this. It usually won't be this. Questions won't give you the change of variables function most of the time. And by way of that change of variables function, it's the image of the unit square in the UV plane. All right, so with all of this given in the statement of the question, we're going to try to do a change of variables. Everybody with me? All right, so again, how does change of variables work? Change of variables is a pullback. We're going to take what we have over here on the right-hand side, and we're going to try to sort of rewrite all of my x's and y's in terms of u's and v's. I have my formula right over here to work off of. Everywhere I see x and y, I'm just going to plug in and rewrite it in terms of u's and v's using the given formulas. I mean, I know this change of variables function g. That's just a matter of plugging in. The tricky part is I'm going to have to figure out what my stretching factor is. But again, I have a formula for my stretching factor. My stretching factor, absolute value of the Jacobian determinant. So let's do that part first. Let's compute my Jacobian determinant. Let's see, here we go. I've got my change of variables function. I can take the partials of x and y with respect to u and v. There's my derivative matrix, easy partials. By the way, make sure to remember the structure of the derivative matrix, right? Input variables correspond to columns. Output variables correspond to rows. Make sure to keep that straight. Stretching factor involves taking the determinant of that Jacobian matrix. No problem. Little algebra. There it is. There's my Jacobian determinant. And the one last little annoying little detail, the stretching factor requires that I take the absolute value of this Jacobian determinant. And here's where you have to pause. Don't move too fast through this part. This absolute value is important. After all, if you think about it, if you look at what does my stretching factor do, my stretching factor's job is to relate this area, which is positive, to this area, which is also positive. So the stretching factor kind of has to be positive. If your stretching factor is negative, something's gone terribly wrong. Right? So always absolute value. Okay, so how do we find this absolute value here? How do we deal with the fact that there's an absolute value? I'd say what a lot of students do is just kind of ignore it and just kind of, forgot it, I guess, right? And just kind of proceed without it. Doesn't work. Important problem in the work. What else am I going to do? And specifically, given our Jacobian determinant, how am I going to figure out whether 4uv minus 9 is positive or negative? Right? I mean, if u and v were big, this could be positive. If u and v are small, then this could be negative. Seems like it could go either way. This is actually surprisingly easy to resolve. All you have to do is look at your pullback domain. Notice that your pullback domain is telling you right there in its picture what's going on with u and v specifically. So for example, u is the horizontal coordinate there. I can see right here in the picture u and v on this pullback domain, on that yellow square. U is always between 0 and 1. So that thing right there, that u, always between 0 and 1. And then likewise, this thing right here, v. Well, there's the v-axis. V, apparently also always between 0 and 1. So what I've got here is two things that are always between 0 and 1, multiplied by 4, still less than 4. And then I subtract 9. That guaranteed makes it negative. Everybody with me? Everybody's happy? Okay. All right. So because of, again, what we see in this picture, I see that this thing, my Jacobian determinant, is always negative, and so therefore its absolute value is the negative of itself. Right? Just a fact to make sure you remember from high school algebra. The absolute value of a negative number is the negative of that negative number. Something to think through. Make sure you're comfortable with that. Yep.
So what happened if it's like minus 3?
Yeah, that's right, and that would make this a much harder problem if that were the case. So when I manufactured this question, I went to the trouble to make sure that wasn't the case. Yeah, no, you're quite right. Looking at this domain over here, looking at the pullback domain, it could happen that there's a line like this. And on this side of the line, the Jacobian determinant's always positive. And on this side, the Jacobian determinant's always negative. And yeah, you'd have to break it up into two separate intervals. And at that point, it's not clear that this is any easier than the question we had in the first place. And we might, in fact, just bail and deal with the original question. Yeah. For whatever it's worth, y'all, of course, have access to all my old midterm exams. And y'all can go through and form your own opinions on how likely is it that I would give a question like that. And I'm not going to comment specifically, but I will say that I think there's pretty compelling data in my old exams of how often that does or doesn't show up. Okay. All right, it's a great question. All right. Okay, so it's kind of all over at this point. We've got our stretching factor. Now it's just a matter of kind of plugging in. I do need to give myself some space here. Let's see here. First, we need to do the plugging in. For example, this x right here from our original integral. What is x? Don't forget that x is part of what the change of variables function is telling you in the first place. I mean, again, keep in mind that this function is literally giving you x and y as functions of u and v, and so, among other things, it is telling you exactly what x is in terms of u and v. Give me 2 seconds. So this x, per this formula right there, this x is just that right there. Yes?
Where did x plus y come from?
Oh, that was just in the original, what the question was asking was compute this integral of x plus y for, so, some application, who knows. Again, this is kind of a phase 2 sort of a thing. Arguably it's kind of just developing the double integral, turning one double integral into a different double integral. Yeah. Right. Okay. All right, so x, right there looking at me in the change of variables function. Likewise, what is this y right here? How am I going to figure out y? Well, y is the other thing that the change of variables function tells me. And so y is that right there. Plug it in. Nothing to it. Hardly anything happened there. I'm kind of just recopying the change of variables function and putting it everywhere I see an x. I put the formula for what x is. Is that all right? Everybody's happy? Don't forget to plug in your stretching factor. Keep in mind your stretching factor is the absolute value of the Jacobian determinant. Just make sure to stick that in there, and we're in business. We have ourselves a new integral. Now, let's take a look at this and ask ourselves, was this a win? Right? Did we help things here? At a glance, you look at this integral and you think, I love that integrand. It's just x plus y. Convenient. Very nice. Right? But what stinks is, keep in mind, you're integrating over this highly undesirable domain. And so the fact that the integrand isn't that bad is little consolation. Whereas this new integral that I've turned it into, now at a glance it looks kind of annoying. It's a great big polynomial, but here's the thing, it's just a polynomial. Polynomials, easiest functions to anti-differentiate. So the fact that it's a big polynomial, really not that big a deal. The big deal is the fact that its domain is super convenient. It's my personal favorite, and perhaps your personal favorite, two-dimensional domain for a double integral. Unit square. 0 to 1, 0 to 1. Constant bounds, world's easiest constants, hard to beat. Right? So this is a big win. We have a much more desirable new integral. Is everybody happy? All right. Okay. So this is the process, pretty much. Now, in this example that we just looked at, recall I confessed that it was a highly manufactured example, right? I gave the change of variables function in the statement of the question, and I gave the pullback domain, again, in the statement of the question. So that did a lot of the work for us. Heads up, in reality, most of the time, the change of variables function will not just be given, right? You have to kind of decide for yourself what your change of variables function is going to be. So I'm going to talk through some examples real quick. I want to remind you, though, when you come up with a change of variables function, don't forget that what you're effectively going to be doing with that is pulling back, going backwards through that function. And so everything's going to kind of sort of seemingly be sort of a little bit reversed. And so, for example, if you have a change of variables function that translates by the vector a comma b, if your change of variables function adds a comma b to all points, in the pullback, your domain will effectively be translated backwards. In other words, be translated by negative a comma negative b. And then likewise, if your change of variables function stretches, well, then doing that backwards will squish. If your change of variables is a counterclockwise rotation, effectively that will clockwise rotate your domain. Now let me show you an example of this latter one, just to kind of point out this this sort of oppositeness that I'm claiming here. We'll get real specific with this next example. And here we go. We've got a domain given. It's a certain square, certain corners given. There it is. There's our domain. You can see why we don't like this domain. No matter which way you slice it, you're going to be hitting corners. In fact, whichever way you slice it, you're going to hit 2 corners. So you're going to have 3 separate integrals. Nobody wants that. This is a bad domain. Everybody with me? I claim that you can think of this as achieved by rotating this square that I'm going to call S. This square S is kind of aligned with the coordinate axes, as you can see here. And just for kind of visual convenience, I'm going to kind of sort of draw its, thinking of it over here, just to be able to see the, kind of what it looks like. So I observe that the blue square is a counterclockwise rotation of that yellow square. Now we're going to have to quantify exactly what is this function, this thing called t, this rotation function that rotates counterclockwise by a given angle, pi over 6 in this case. And again, notice these vertices are all given. A little bit of geometry will persuade you that this angle is pi over 6. Can I figure out that formula? But when I do the pullback, the original integral that I had, this original integral over d, the original integral over this blue domain is going to turn into an integral on the yellow domain. In other words, we are going to be going the opposite direction. What we will accomplish with this counterclockwise change of variables function is we will accomplish that our domain will effectively get rotated clockwise. Everybody see what I mean? Okay. It's all details from here on out. Let's talk about how to do a rotation. Now this, again, I hope that this is all Math 218 familiar. Keep in mind rotations are linear transformations. Linear transformations are understood by their matrices. Matrices are understood by their columns, and the columns are the images of the standard basis vectors. Y'all heard me say this a bunch of times. It's a really important fact of linear algebra. And it's not just rotations, right? Reflections also. Any linear transformation on the plane, a shearing transformation, for example. Plenty of other kinds of, magnifications, a lot of them, right? Understood by matrices, which are understood by their columns, which are the images of the standard basis vectors. So I want to make sure everybody is good with how to do that linear algebra. If you are unclear with what happened here, right, come to my office hours. I'll be very happy to, we'll take our time, we'll go through it as needed. I want to make sure that everyone's comfortable with how to do this. Now we've talked about rotation specifically in a previous context, so I'm just going to, kind of wave my hands flashing back to that previous discussion that this is what the matrix looks like, and given this this angle being pi over 6 specifically, that makes the matrix this right here. So I hope that all looks familiar. Oh, and don't forget there was, and I'm sure you haven't, but on the first midterm exam there was a rotation matrix. Maybe exactly this one I've already forgotten, but something certainly very similar to this. Okay, so anyway, make sure that you're good with this. And the nice punchline then is here's my rotation. It's given by this formula. This is the relationship that turns u's and v's into x's and y's, or said differently, that gives my formulas for x's and y in terms of u and v. Happy? All right, let's compute our stretching factor. Stretching factor comes from the Jacobian determinant. This thing here, determinant of that Jacobian matrix. It's not hard to take the Jacobian of this function. By the way, weird phenomenon. The matrix that represents this linear transformation It's Jacobian. What are the odds? Same matrix. Weird. Turns out that's always true. Neat fact. And I can't remember. I think I may have made that a homework exercise. You either will notice that sometime soon, or I may be mistaken. But either way, I think this is a useful exercise. Nice fact. Whenever you have a linear transformation represented by a matrix, the derivative of that transformation is the same matrix. Anyway. Okay, so proceeding along, keep in mind we want the determinant of that derivative, and it turns out to be 1. Now, what are the odds? How weird is that? I mean, there were square roots and fractions all over this calculation. How did it turn out to be exactly 1? Was this a coincidence? Turns out no. And if you think about it, in fact, not only is it not a coincidence, it's sort of obvious that this will always happen if you're talking about a rotation. After all, rotations don't make things bigger nor smaller. Rotations keep areas exactly the same. So, not surprising, and in fact, expected. Does that make sense to everybody? Now, that said, even though it is expected, this being a class in which, the material that I want y'all to demonstrate understanding of is the ability to compute a Jacobian determinant, I do want to see the calculation. In Math 219, you got to give me the calculation, right? But outside of Math 219, if you're rotating for change of variables, free Jacobian determinant, definitely 1, and all good. All right. Okay, it's all over but the shouting. Here's my Jacobian determinant. It's a 1, nothing to worry about. Now I got to plug in for my x and my y. There's an x right there in my integrand. Where am I going to get x from? Well, again, don't forget the change of variables function itself is telling you x and y, and so among other things, x as a function of u and v. So right here from this matrix multiplication, x is that. And likewise, this y right here is that. Whoa, almost overshot it. There we go. And so my original integrand, 2x minus y, becomes all of this, 2 times that big thing minus that big thing. That's just plugging in. Hardly anything happened. Right? Using the formulas given in the change of variables function to just literally plug in. I've already inserted my stretching factor, and we're in business. We have ourselves a new integral. Let me clean up the mess here. My original integral here on a highly undesirable domain that I didn't want to have to deal with has now been rewritten as a new integral over a much nicer domain. And okay, I'm going to confess that the integrand's a little weirder. Small price to pay, right? Rather than a linear polynomial with integer coefficients, now I have a linear polynomial with not integer coefficients. That's a really small cost, but I only have a single integral to compute. I have constant bounds, rectangular pullback domain. Again, big victory. I just cut the workload by a factor of 3. How we doing? Okay. So a couple of formalities I need to get said. In order for everything to work out, I do need my change of variables function to be continuously differentiable. And it's just, if it's not, then your integrand's not continuous. We haven't defined integrals for non-continuous integrand. Anyway, no big deal. The other thing is it does also have to be invertible. And I want to draw a quick picture just to give you enough rough idea why it needs to be invertible. If it's not invertible, here's what you would have to worry about. What if your pullback domain is like that, and its image, now here begins the art challenge for me. What if the image did this move right here? All right, and what's going to happen if that's the case is, let's see here. Whoops. This region here maps over to, well, it's all of this for a little while, and then eventually, as it proceeds along, oh, I shouldn't have made this so big, but it's going to double over itself. Right? You can see we've kind of double counted. We've overlaid this little region here twice. Right? So if you had an integral on this set, then the points in this region should count once. But by viewing it as the image of this, we're effectively counting it twice. And so anyway, this kind of nonsense also technically you have to avoid. Good news, we're not going to encounter any of this kind of stuff in this course. So I'm going to mostly sweep that under the rug. But just a heads up, for the sake of thoroughness, I just wanted y'all to be aware that that is technically an issue. Okay. All right. Now, I have a few more examples to show you. We were very explicit when we wrote down our method here that whatever direction the function goes, we will be pulling back. The opposite of the direction of the function. But what if you can't get the function going the correct direction? What if the function's going the wrong way? What if your function is going to the left and you want to, again, sort of take the integral in that same direction? Does it work? Well, it kind of sort of has to work in some sense, because if you look at the way this is written, notice that this is this is an equal sign. An equal sign works both ways. Right? So the problem is not that you can only go this way. It's that it's set up to most conveniently go this way, but again, equal signs really are. If A is equal to B, then B is equal to A. So you can, in theory, go any direction you want. Main problem being, we only know a formula for the stretching factor that way. Right? So, what I'm going to do is talk about how to compute the stretching factor in the other direction. And it turns out there's a lovely little answer. Now, old news that we've already established, if your function is like this, and so, you've got output variables, x and y, and input variables, u and v. Our stretching factor is partial of the outputs over partial of the inputs. That's the rule. And so there's our formula for our stretching factor going to the right. Now let me set that aside. Let's momentarily forget that this is what we know. Let's scratch that off. Now let's pretend just momentarily that we have a function going that way. What is the stretching factor in the pullback sense if the function's going that way? Well, stretching factor is the partial of the outputs. This time u and v are my outputs. With respect to the inputs, this time x and y, as those are our inputs. So the stretching factor for the function going the opposite direction is it's like I kind of did a switcheroo on the numerator and the denominator. So it seems. Let me remind you, of course, this is not a fraction. There is no numerator, there is no denominator, that's notation only. So nevertheless, though, this is the formula for the stretching factor going the other way. And now I argue as follows. If I had some little piece of area over here, and if I push forward, I don't know what area that will be, but then if I immediately then also come back, altogether, this little green piece of area, go forward, you come back, it's the exact same little green piece of area. So altogether, the stretching factor of the product is just 1, because the green area goes to exactly 1 times the green area. Right? And so the good news, even though this is not technically a fraction, it behaves in this sense also, like a fraction. Not only in the cancellation sense that we talked about previously, but this actually behaves fraction-wise, like a fraction. And that's a really important fact. That's going to be the foot in the door that allows us to do this next example, which we don't have time for, but we will pick up here on Monday. Y'all have a great weekend. See you later.